All right, guys. So what I want to do here is just basically continue the review we were working on. And in lieu of me in WebEx, you'll just continue alongside with me, fill in the gaps that I ask you to, and submit the review when the time comes and uh, you have all this completed. We'll pick up where we leave off here when I come back on Thursday. All right, so I believe that we left off. We probably finished some of this with some of my classes, but make sure that everyone's caught up with everybody. I'm just going to go ahead and start at number 30 so that everyone's on the same page, okay? So, besides tangent lines being perpendicular to radii forming right triangles which follow the Pythagorean theorem, tangent lines also have another property. Specifically, when tangent lines are from the same point to the same circle, they end up being congruent. So for instance, here we know that x is equal to 22 because these two tangent lines, JK and JM, must be congruent. Okay? Likewise, for 31, since these two lines are tangent to circle L and from the same point J, I know that JK must be congruent with JM again. Therefore, 3x will equal x plus 12, which would yield, looks like x is equal to 6. Okay, I will leave you to finish up 32 on your own. I want to see it done in your notes. Okay, let's look at 33 together. Okay, on a softball field, the home plate is 38 feet from the pitching circle. Okay, this is the pitching circle, and we're 38 feet away from it. Okay, that's my line there. Oh, okay, good. Home plate is about 45.3 feet from a point of tangency on a circle. So we know that this must then therefore be a tangent line. A is asking, how far is it from the home plate to a point of tangency on the other side of the pitching circle? Well, that would just be this line here, right? And since it's tangent to the same circle and it's from the same point, what do I know about this tangent on top and this tangent on the bottom? Well, they of course have to be congruent again, right? So of course this would simply be 45.3 feet as well. B is asking for the radius of the pitching circle, so it's synonymous with a problem that we have done earlier in 27 through 29. Okay, so the radius of the pitching circle, let's go ahead and do that. Remember, this is a right triangle which follows the Pythagorean theorem, heralded most likely to be remembered as a piece of information from high school. Okay, so anyway, we have R, which could act as A. We have 45.3 feet. Oops. Which could act as B, and we are looking for the hypotenuse, which contains R, so that would be R plus 38 squared. All right, so I'm going to leave this, well, I'll work it out a little bit for you, but I'll leave most of the calculation to you, as I don't have a calculator built onto this iPad. Remember that you have to FOIL this out. Okay, so first outer inner last, remember, so if R squared, we'll have, looks like what, 38R plus 38R would give us 76R, is it? And then I don't know what 38 squared is, but you'll have to figure that out for yourself. Luckily here, r squareds cancel, and you can take care of the rest. Finish it up in your notes, please. Okay, we'll do some more in section 2. Name the arc shown in bold. So we are just naming these arcs. They want us to name arc that's shown in bold. That would simply be arc AB. And that is, of course, a minor arc. Okay, here they want us to name this arc, and it is a larger arc, certainly larger than 180 degrees, which would make it a major arc. And major arcs would require us to use 3 letters. Okay, 3 letters. So we're going to go ahead and call this arc ADB. Okay, here we have another arc. This one is actually a semicircle, which is specific because that means it measures 180 degrees, which is sometimes useful. Formed by a diameter, by the way. You could name this better safe than sorry. Let's go ahead and name this arc PSQ. If I had said PQ, you wouldn't have known if I was talking about this arc or you know, that arc on top. Okay, let's do some of this. I'll do the left-hand side here, and you guys go ahead and finish up with the right-hand side. Okay, so AE is this arc, certainly less than 180, so I would say that it is a minor arc. Now they want FDE. FDE, I have to go around the circle, shortest distance to the letter there. Okay, that looks like it's a semicircle. All right, FA, well, that's just that much right there. That's certainly a minor arc, less than 180. BDA, it looks like another semicircle. All right, so remember, if it's less than 180, we're dealing with a minor arc. And if it's greater than 180, we're dealing with a major. And if it's equal to 180, we're dealing with a semicircle. Okay. Now, remember that diameters form semicircles, which are 180-degree arcs. They'd be super useful here. So they tell us the MQ and NR are diameters, and that's going to be my ticket right there. Find the indicated measure. I'll do some of these. I want you to finish them up. So let's take a look at MN. Arc MN would come from its central angle measure here, which is 70 degrees right there. Okay. 13 NQ. NQ is right here, and I know that MN is a semicircle. Sorry, it's a diameter rather, which makes MNQ a semicircle, 180 degrees. So this would be equal to, I would say, 180 minus what we're not counting here, which is 70, which would give me 110. All right. NQR. Okay, well, that's this again. And R is the diameter, so that's just going to be 180 degrees. All right. MRP. Okay, well, we know that this much here, we'll do it in red perhaps. This is 180. And since this central angle is 30, then this arc must also be 30. So that will be equal to 180 plus 30 for 210.